Okay, so you're here because you want to understand complex stuff, right? You want it fast and you want all the details.
That's exactly what we're all about.
And today we're diving deep into graph neural networks, sometimes called MPNNs.
MPNNs, yeah.
They're everywhere now. I mean, literally from designing drugs to forecasting weather to cracking those insane optimization problems, right?
It's incredible how well they work across all these different areas. I mean,
Yeah.
getting actual real-world results. But here's the thing. If we zoom out a bit, the theory behind why they're so good, especially at predicting things on data they've never even seen before, well, that's still kind of a work in progress.
Yeah.
And that's exactly what we're going to explore in this deep dive.
Right. We see them doing these amazing things, but how can they predict stuff they weren't explicitly trained on? We've got this awesome survey paper that goes through all the current research on this whole MPNN generalization thing.
Yeah, it's really comprehensive.
So think of this as your super fast track to understanding where we're at with the theory right now.
So, for everyone listening, what are the big ideas we need to wrap our heads around to understand this whole theoretical landscape?
Yeah.
We're going to be looking at this interplay between expressivity, what these networks can actually represent, and generalization, what they can actually do with new information.
Yeah.
And we'll also be checking out all the different theoretical tools that researchers are using to analyze this ability to generalize.
So yeah, we're going to hit things like VC dimension,
Mm-hmm.
Rademacher complexity,
Yep.
PAC-Bayesian methods, covering numbers, even stability. And because this field is moving so fast, we'll also look at the newer stuff like transductive learning and how MPNNs deal with data that looks different from what they were trained on, right? So that's out of distribution generalization.
Right.
But the goal here, like always, is to pull out the most important insights from these often pretty technical discussions. And we
Right.
want to present them to you in a way that just clicks so you get those aha moments
Right.
without getting bogged down in the crazy details.
Exactly. Sound good. Okay. So first things first, we need to get this distinction between expressivity and generalization. What's the core difference there?
So, think of expressivity as the range of ideas that an MPNN can understand or distinguish, right?
Uh-huh.
It's about its capacity to tell different graphs apart or to approximate different kinds of relationships on those graphs. And this is an area where the theory is a bit more established. It's often linked to this thing called the one-dimensional Weisfeiler-Lehmann algorithm, or 1WL.
Yeah, the 1WL algorithm, it's a pretty clever method for figuring out if two graphs have different structures.
Okay.
It works by repeatedly refining the labels of each point in the graph, based on the labels of its neighbors.
Right.
So if after a few rounds of this, the patterns of labels in two graphs are different, well, then we know those graphs aren't actually structurally the same.
And here's where it gets really interesting, right? Because the ability of an MPNN to tell graphs apart, it's in a way limited by what this 1WL algorithm can do. If the 1WL can't tell two graphs apart, then no MPNN, no matter how fancy it is, will be able to consistently tell them apart either.
Yeah, exactly. The limitations of the 1WL in distinguishing certain types of graphs, like ones that are structurally different, but the 1WL can't tell them apart,
Right.
that directly limits how expressive MPNNs can be. But, just because it can represent complex relationships, that doesn't mean it's automatically going to do well on new data, right?
Yep.
And that's where generalization comes in.
Totally, yeah.
A really expressive model might just memorize the training data and then, completely fail when it sees something new.
Right. So, how do we even begin to, theoretically understand this ability to do well on data it hasn't seen before? That's where all these theoretical frameworks come in.
Right.
So let's start with VC dimension, right? What's the basic idea there? How are we using VC dimension to understand how well MPNNs generalize?
So VC dimension is a way to measure the capacity of a bunch of possible models. In our case, that'd be all the different MPNNs with a particular architecture.
Okay.
And it aims to give us an upper limit on how much the model's performance on the data it was trained on might differ from how it performs on all possible data. It's about understanding the worst case scenario.
And the fact that they're using VC dimension theory for these MPNNs, it's pretty interesting, right? I remember reading that some of the early work connected it to recurrent neural networks, which seemed kind of surprising because graphs feel way more complex than sequences.
Yeah, it is interesting. The initial limits they found for MPNNs using VC dimension, they did have some similarities to those for recurrent neural networks.
Yeah.
And that might seem counterintuitive, right? Because graphs are way more intricate than simple sequences.
Right.
But the mathematical tools they use, they often rely on similar ideas of combining functions and counting the number of parameters you can adjust.
Yeah.
But more recently, researchers have been looking at more sophisticated MPNN designs.
Yeah.
And these new limits consider things like how many parameters there are, how deep the network is, the size of the feature vectors, even the size of the graphs themselves.
So we're getting a more detailed picture now, right? Like how these design choices affect the model's capacity as measured by this VC dimension.
Right.
And I understand there's a link being made between this VC dimension and that 1WL algorithm we talked about before, right?
This is where it gets really interesting, actually. Recent work has found a direct connection between the 1WL and the VC dimension, at least for a specific type of MPNN.
Okay.
It turns out the maximum number of different graph structures that the 1WL can tell apart after a certain number of steps, that also acts as an upper limit on the VC dimension of these MPNNs.
Whoa, that's a pretty elegant connection. So the thing that's limiting what the MPNN can express in terms of like recognizing different graph structures, it also limits its ability to generalize in this like perfect worst case scenario. So it's like this fundamental trade-off, right?
Exactly. And what's more, research shows that if the MPNN has enough capacity, what they call sufficiently wide networks,
Right.
it can actually shatter all the graphs that the 1WL can distinguish. So think of it like this. If the 1WL can tell the difference between, say, 10 different types of graphs,
Uh-huh.
a powerful enough MPNN can shatter those graphs, meaning it can learn any possible labeling you could give those graphs.
Wow.
So the 1WL's expressivity limit basically becomes a direct measure of the generalization capacity in this specific theoretical framework.
That's a really powerful insight, right? Like it suggests that just the basic limitations in like telling graph structures apart might actually limit how well we can learn to classify them.
Right.
Now, I also saw this thing called R separability and partial concepts. Like, how do those fit into this whole VC dimension thing for MPNNs?
Oh, those are interesting extensions.
Yeah.
So with R separability, you're basically looking at situations where the classification task isn't perfectly clear-cut.
Okay.
Like imagine you have some data points and you want to separate them with a bit of a buffer zone. That's the R.
Right.
And then you allow for some flexibility in how well they're separated, like a certain rate at which the separation can get worse. And that's controlled by the R.
Okay.
And, you're trying to separate these points using a function that comes from our set of MPNN models.
Oh.
Partial concepts, on the other hand, are all about cases where our MPNN might not even be defined for every single possible graph.
Mm-hmm.
Researchers have shown that we could adapt VC dimension analysis to handle these more complex scenarios for MPNNs. And what's cool is that some of the limits they've found might not even depend on the initial information we have about the nodes in the graph, which is pretty significant.
Okay, so that gives us a good overview of the whole VC dimension approach. Now, another framework that keeps popping up is this Rademacher complexity thing, right? So how's that different from VC dimension in like how it tries to understand generalization?
Well, the main difference is that while VC dimension gives us this general data-independent way to measure how capable our models are, Rademacher complexity actually considers the specific data we're working with.
Okay.
So instead of looking at every possible data set, it focuses on how well our set of MPNN models can fit random, meaningless labels to our actual training data.
Okay, so fitting random noise
Yeah.
sounds like something we don't want, right?
Right.
So does that mean that a higher Rademacher complexity means there's a higher risk of overfitting? Where the model learns the training data too well, including the noise, and then doesn't generalize as well?
Exactly. If our models can easily fit random labels, it suggests they have enough flexibility to fit like random patterns in real data that don't actually mean anything, things that won't actually help them generalize. The bounds on generalization error that are based on Rademacher complexity, they essentially say that the actual error we'll see on new data, it's probably not that much worse than the error we see on the training data.
Okay.
Plus a term that depends on the Rademacher complexity of our MPNN models. So in essence, Rademacher complexity tells us how likely our model is to get tricked by noise in our specific data set, which is like super important for avoiding overfitting.
And I saw that there are data-dependent Rademacher complexity bounds specifically for MPNN architectures. So that sounds like it could give us more accurate estimates than these like more general VC dimension bounds?
Yeah, for sure. Researchers have developed data-dependent Rademacher complexity bounds that are tailored to specific MPNN designs.
Okay.
And interestingly enough, these bounds often look a lot like the ones they've developed for recurrent neural networks, which is a pretty cool connection.
Yeah.
And these bounds, they usually take into account factors like the architecture of the network, so like how the adjustable parameters work, the nonlinear functions they use, and how they combine information from neighboring nodes.
I also noticed some results that linked this Rademacher complexity to like how confident the model is in its predictions, right? What they call margin-based loss functions.
Uh-huh.
And even for specific types of MPNNs, like these graph convolutional networks or GCNs. So what kind of things influence those bounds?
Yeah, there were definitely some interesting results that connect Rademacher complexity to the confidence of the model's predictions.
Okay.
For GCN specifically, the bounds often depend on things like the type of nonlinear activation function they use, how big the feature vectors are, the properties of the graph filter using the convolution operation,
Right.
especially the eigenvalues, and even just like the number of connections each node in the graph has, which is called its degree. So, all these factors give us a much more detailed understanding of why some GCNs generalize better than others.
Okay, so we've looked at these like capacity-based measures like VC dimension and these data-dependent measures like Rademacher complexity.
Right.
Now let's shift gears a bit and talk about these stability-based bounds.
Okay.
This sounds like it takes a different approach entirely, right?
Yeah.
Like it's looking at the learning process itself.
Exactly. With stability-based bounds, we're not just analyzing the complexity of the set of possible models anymore.
Right.
We're looking at the properties of the algorithm we use to train the MPNN, things like stochastic gradient descent or SGD.
Right.
The main idea is to see how much the model we learn changes if we just slightly tweak the training data, like by taking out a single data point.
So a more stable algorithm, one where the model doesn't go crazy when we make a tiny change to the training data,
Yeah.
that would be expected to generalize better.
That's the general idea. The concept of uniform stability is basically a formal way to measure this.
Yeah.
It looks at, like, the maximum change in what the model predicts when you remove any single data point from the training set.
Okay.
And researchers have actually used the stability properties of simpler single-layer GCNs to come up with generalization bounds. What's interesting is that some of these bounds suggest that the generalization error might actually go up as you add more layers to the network.
Oh, that's a really important point. So it could explain why sometimes making a GCN deeper doesn't actually help it perform better on new data, right? Even though it might be able to represent more complex relationships. Like the instability from adding more layers might outweigh the benefits of being able to represent more stuff.
Exactly. These stability-based analyses give us a different way to understand generalization, by focusing on how the learning process itself behaves, rather than just looking at the model itself.
Okay, now let's dive into this PAC-Bayesian framework. This sounds like it brings in some probability theory to the mix.
Yeah, it does.
So what's the deal with that?
The PAC-Bayesian approach is a bit different. It starts by assuming we have some initial beliefs about which MPNN models are likely to be good.
Okay.
And we represent those beliefs as a probability distribution over all our possible models, which we call the prior.
Right.
Then, once we've seen the training data, we update these beliefs to get a new probability distribution, which we call the posterior.
Okay.
And the generalization bounds in this framework, they're based on how much our beliefs have changed after seeing the data. To measure this change, we use something called the Kullback-Leibler divergence, or KL divergence for short.
KL divergence, okay.
Well, think of KL divergence as a way to measure how surprised we are by the training data, given what we initially believed about good models. If we're really surprised, it probably means our initial beliefs were off.
Okay, so if our initial beliefs were pretty accurate and the training data doesn't like completely flick our world upside down, meaning the KL divergence is small, then we might expect to see better generalization.
Exactly. And researchers have developed specific PAC-Bayesian bounds for multi-layer GCNs and other MPNNs.
Okay.
These bounds often depend on things like the maximum number of connections any node in the graph has and the size of the weights in the model. And it turns out that for MPNNs, these PAC-Bayesian bounds can sometimes be more accurate than the ones we get from Rademacher complexity.
I remember seeing something about efforts to make these bounds better, right? Like to deal with some of their limitations, such as this issue with nodes having lots of connections.
Right. There's been some work on refining those bounds.
Yeah.
For example, reducing how much they depend on that maximum number of connections, which makes them more useful in practice. And the PAC-based framework has also been used in other areas, like understanding the representations that are learned for knowledge graphs, which is another area where graph-based models are super important.
Right.
It's also worth pointing out that we can even use the PAC-based framework to analyze models that aren't probabilistic by adding a bit of randomness to them, which is a pretty cool trick.
That is a cool trick. All right, so moving on to covering number-based bounds. This sounds like it's bringing in some geometry concepts, right?
Yeah, it kind of is.
So, like, how does that work?
This approach tries to define a way to measure how similar two graphs are.
Okay.
And we want to do it in such a way that MPNNs behave nicely with respect to this similarity.
Right.
So basically, we want them to change their output in a predictable way when we make small changes to the input graphs. And if we can also show that the entire space of possible graphs is compact,
Okay.
meaning we can cover it with a finite number of small representative graphs under this measure of similarity,
Right.
then we can figure out generalization bounds based on how many of these representatives we need. That's called the covering number.
So basically, we need a way to measure how close two graphs are that guarantees the MPNs will give similar results for similar graphs. And then we need to know how many typical graphs it takes to represent all possible graphs.
Exactly. There are basically two ways to approach this. There's the uniform regime, which tries to consider all possible graphs, no matter how big they are.
Okay.
This often uses fancy mathematical tools like graphon theory, where you treat graphs as samples from a continuous structure called a graphon signal.
Okay.
Measures of distance, like the graphon signal cut distance, are used to establish that compactness we talked about and ensure the MPNNs are well behaved.
Right.
The bounds are then based on how many of these graphon signals you need to approximate the whole space of graphs. There's also an alternative approach in this uniform regime that uses things called iterated degree measures, or IDMs.
So what about the non-uniform regime? That
Yeah.
sounds like it focuses on graphs of a specific size.
Exactly. In the non-uniform regime, we usually look at a finite set of graphs, like all the graphs that have, say, 10 nodes.
Right.
Since there are only a finite number of them, the space is automatically compact for any reasonable measure of distance. Researchers might use combinatorial techniques here and focus on things like how different the tree structures of two graphs are to analyze how equicontinuous the MPNNs are, which is a slightly weaker form of being well-behaved.
Okay.
They then connect the idea of a robust learning algorithm, meaning one that doesn't freak out when you make small changes to the data,
Right.
to covering numbers, which then leads to generalization bounds. And they've even extended this approach to handle graphs where the nodes have extra features and MPNNs that use a simple average to combine information from neighboring nodes.
And I also saw something about generalization bounds for mixtures of generating graphons.
Oh, yeah.
That sounds like it's making some specific assumptions about how the graph data is actually created, right?
You got it. That approach basically assumes that all the different graph data we see can be modeled as coming from a limited number of template graphons, combined in different ways. And each template is like a blueprint for creating random graphs. So in a classification task, the idea is that if two graphs were generated from the same template, they probably belong to the same category.
Okay.
And using this assumption, we can derive limits on how well our MPNN will generalize.
Right.
Interestingly, these limits often suggest that MPNNs do better on new data when the graphs in the data are larger.
Interesting.
But of course, we have to remember that these bounds only really apply if this specific model of how the graph data is generated is actually true.
Makes sense. So that's a pretty good rundown of the covering number approach and its different variations. Now let's move on to transduction in graph learning. How does that differ from this, like, inductive learning stuff we've been talking about so far?
So inductive learning is all about learning a general rule from some examples that you can then apply to any new data you come across.
Right.
Transductive learning, though, it's specifically about making predictions for a specific set of data points that you actually have access to during the training process. So the goal isn't really to generalize to every single new graph you might see in the future. It's more about making the best predictions for this particular set of test examples that you already have.
So it's like you've got all the data you're interested in, you know the labels for some of it, which is your training data, and you want to figure out the labels for the rest, which is your test data.
Exactly.
But you're not really expecting to encounter entirely new graphs later on.
Right.
Okay.
The way we analyze this statistically is by treating the labeled data as a random sample from this fixed set of all the data we care about.
Okay.
And that changes how we think about generalization. Instead of the usual Rademacher complexity, which only looks at the training data, we use transductive Rademacher complexity, which takes both the training and test data into account.
And have people been able to use this transductive Rademacher complexity to get bounds on how well these MPNNs will do in this setting?
Yep, they have.
Oh.
There are generalization bounds that have been derived using transductive Rademacher complexity for specific types of MPNN architectures. And these bounds naturally depend on the structure of the entire graph, how all the nodes are connected, because the test set is part of the whole picture.
Right. Okay, last but not least, let's talk about this out-of-distribution generalization challenge, right? This seems like it's really important for real-world applications where the data we see after we've trained our model might not look anything like what we used to train it.
Out of distribution generalization, yeah, it's a big one. It's basically when the training and test data come from totally different processes. And a lot of the traditional generalization bounds, which usually assume that the training and test data come from the same source, they don't really apply here.
Which makes sense if the underlying rules that govern the data have changed between when we trained the model and when we're actually using it, then our guarantees about how well it'll perform might be completely out the window.
Exactly.
So what are people doing to try and solve this problem for GNNs?
Well, figuring out and understanding O generalization for GNNs is a really hot research topic right now. Some approaches use ideas from information theory to try to quantify how different the training and test data are. Others use techniques from causal machine learning to try and figure out and minimize the effects of hidden factors that might be different between the two data sets. And there's also a lot of focus on how well GNNs can handle graphs of different sizes than what they were trained on,
Okay.
sometimes called size generalization or size transferability.
Okay.
Continuous representations of graphs, like those graph arms, are proving really useful here,
Right.
as is looking at those small recurring structural patterns in graphs, called D patterns, to try and understand the size-related differences between the training and test graphs.
So it sounds like O generalization is a really cutting-edge area where we're still figuring a lot of stuff out.
Yeah, it's a big challenge, but super important for making sure that graph neural networks are reliable in real-world situations. Yeah. Because, the data you come across in the real world is often very different from what you trained your model on.
Right. Well, this has been an awesome deep dive into all the theoretical stuff behind how well MPNNs can generalize. We've covered a ton, from the basic concepts of expressivity and generalization to all the different theoretical tools people are using to understand why these networks work so well.
Yeah, it's been really interesting to see how these different frameworks like VC dimension, Rademacher complexity, PAC-Bayesian methods covering numbers, stability analysis, and transductive learning, they all offer unique perspectives on the generalization capabilities of MPNNs.
Yeah.
We've definitely come a long way, but it's clear that there's still a lot we don't know, and there are a lot of important challenges ahead.
And understanding all this theoretical stuff isn't just for academics.
Definitely not.
It's super important for developing MPNNs that are more robust and dependable, ones we can actually trust to use in real-world applications where the stakes are high.
Right. And that leads to some big questions about the future of the field.
Yeah.
We need to keep working on bridging the gap between how well MPNNs can represent information and how well they can generalize to new situations.
Yeah.
Coming up with more accurate and practical bounds on their performance is crucial, as is getting a better handle on how they deal with data that's different from what they were trained on.
Absolutely. So as you're listening to this, think about how the specific structural features of the graphs in your field might affect how well MPNNs can generalize.
Yeah, that's a good point.
Which of these theoretical frameworks might be most helpful for understanding how well they'll perform in your specific applications. And we really encourage you to dig deeper into the research we've talked about today, explore the areas that you found most interesting. Thanks for joining us on this deep dive.
Yeah, thanks for listening.